Hello, everyone, and welcome to the next part of this OHBM educational course where we're going to talk about data processing and analysis, specifically looking into different aspects concerning software, standardizing workflows, statistical modeling, and multiverse analysis. As you had already gathered from the sessions and talks before this one, we are basically focusing on the entire life cycle of a project and the respective steps you usually conduct within there. We already went through project creation and data acquisition, where we learned that, for example, making sure your data is shareable and standardized in a common form and structure is super important. And here we're going to focus on the next two aspects of this life cycle, specifically analysis and results, with communication, dissemination, outreach following after this one. And the basic thing we're trying to tackle here, we want to communicate to you, is that there's a specific problem statement when it comes to data processing analysis within the light of open reproducible neuroimaging. Because usually what we see and are aware of is there are some ideas and hypotheses and some components of a research project, and at some point we get results in a fancy presentation or journal. However, what we usually don't get at all is all the different things the researchers do during the project, all the different avenues to try to explore, and everything that basically led up to the presentations of the results. And regarding this, let's imagine the following scenario. Your BI tasks you to do a couple of analysis for a new project. And lucky enough, you learned that one of your colleagues did run comparable analysis in the past and is actually nice enough to share with you. And even better, everything is assembled in one handy script called fancyanalysis.py. Then your colleague tells you to run the script by navigating to a respective folder and type python fancy_analysis.py, i.e. executing, running the respective script. This is fantastic, amazing. You can actually relax, don't have to do really much at all, and let the script do the work, as it will just run on your data and the computational environment you're using. Or is it? Actually, that's not the case at all. The script immediately produces errors. It doesn't work on your data. It doesn't work on your computational environment. You cannot reproduce anything. So what is going on? And I think this is a common case that we all have experienced one or more times so far in our careers. Well, what's actually going on here? And here's the thing. Usually when you see these kind of things, like you get a script from your colleagues or you find it somewhere out there on the internet and then try to run it on your data and it doesn't work, the usual response you will get is, oh, well, it works on my machine from whoever shared the script and or tool with you. And this is not a thing that only concerns a few of us. It actually concerns all of us. And the problem is actually way bigger in scope than you might initially think. I'm pretty sure most of you by now heard about the reproducibility crisis in FMI, with all of these different outlets indicating, and actually by now, real studies, papers, observations, quantitative analysis, that a lot of the things we do on a daily basis in neuroimaging research is actually not reproducible at all. And why you might think, oh, this relates to certain design choices, analysis choices, and so forth. It's really like the tiny things where you can get lost. It's actually way more prominent than that. Because, for example, in this paper from Glador 2015, they show that if you run the exact same pipeline and on the exact same data, and you only vary the underlying operating system, so you go from Windows to Mac to Linux, for example, this will introduce statistically significant variations in your outcomes. So here they used it on cortical thickness, if I'm not mistaken, which compared to other measurements is like a bit more direct, as you might say. So you would expect it to perform reasonably well and not introduce these kind of variational effects. But that's just what it is. That's just the case. And the question then will become, which results do you trust? Which results do you report? Which results are true? And so far, and until now, and we just don't have any means to actually explore this. So what is happening regarding all of these things? There are, of course, unintentional mistakes, the garden of forking paths because of all of these different options to run data processing analysis. There's, of course, questionable research practices and p-hacking. There's fraud and publication bias, all of these things, which actually led to the number of retraction notices shooting up tenfold in the past decade, as you can see here. However, within this presentation and within our course, we cannot focus on all of these different things because we just simply don't have the time. Well, instead, we're going to talk about the unintentional mistakes in the garden of forking paths. That is, things you might not be aware of regarding your computational environment and data processing and analysis, and the garden of forking paths introduced for all of these different tools we have out there. If you think about data processing analysis a bit further, you actually can summarize it nicely in the way the Turing way did it here by two design analysis and data, where it's either same or different. If we run the same analysis on the same data, we talk about reproducibility. If we run the same analysis on a different kind of data, we talk about replicability. If we run a different analysis on the same data set, it's robustness. And if we run different analysis on different data, it's generalizability. And there were and are new methods proposed regarding all of these different aspects, each quadrant here, for example, sensitivity and robustness analysis, multiverse analysis, specification curves, regression of effects, and sample approaches, basically aiming to tackle and investigate one or more of these quadrants. In the first instance, however, we're going to focus on the same data, same analysis as the most underlying crucial thing, talking about reproducibility. When we talk about science reproducibility, we have to be aware that each and every single project in the lab depends on a complex software environment. This ranges from your operating system, different drivers you have on there, to then software dependencies like Python, R, MATLAB, and the respective libraries that you might want to use or going to use within them. And what you try to avoid here is basically cases like those you can see here. For example, saying, oh, the computer I used was shut down a year ago. I cannot rerun the analysis from my publication. The analysis were, for example, run by my student. I have no idea where and how this was done. All of these things are very common. And there's actually more or less straightforward ways to tackle those things. But you definitely want to try to avoid this because you're introducing dependencies that are not scale up to and hold up to scientific standards. And further talking about, still focusing on reversibility here, things that, for example, can happen if you use a different computation environment, so you've either changed the operating system, drivers, software libraries, is that you might face intrinsic numerical errors and instabilities, so that these errors may lead to unstable functions that go towards distinct local minima. So, for example, things, or put differently, certain functions in computations are not as precise as you might think they are, and there is some variation to that. And especially if you switch one of these different computational environment aspects, those variations might become more significant. Furthermore, as already outlined, we have these primary difference between operating systems, and we know that the tensor stability relates to variability. So the more you vary your computational environment, the higher the chance that you introduce some sort of variability that leads to a different outcome down the line in your pipeline. Furthermore, focusing on and talking about collaboration with your colleagues and everyone else out there, because if you are nice enough to actually care about these things and you want to help other people out, making your analysis reproducible, more maybe even transferable to other people's use cases, if you want to share your code using a repository to do that, this might not be enough. And by all the cases we have seen, usually it won't be enough due to all the aforementioned reasons. And what you try to avoid here is things like, I forgot to mention, you have to use certain software, let's say CLang or GCC that never worked for me. Things like, oh, I don't see any reason why it shouldn't work on Windows, where I actually want to say, I have no idea about Windows, but I want to say it. It's like, that's me, basically. However, I can tell you have no idea about Windows, and will also be more straightforward than. And there's many more like these use cases. Because the thing is, if you have an application working in one computational environment, most of the time you can just not simply transfer it to a different computational environment and reproduce the exact same results. However, throughout the last couple of years, there were different solutions proposed to this problem. And one we're going to focus on here is called virtualization, specifically virtualization technologies, because they aim to isolate the computing environment you're using and provide a mechanism to encapsulate these environments in a self-contained unit that you can actually run anywhere on different machines' computational environments. So you reconstruct the computing environment and then share this computing environment, inserting them at certain layers of your machine. So now let's have a look at the different dimensions of academic research where this would be important and or helpful. So first, we're gonna think about in the project dimension or the researcher dimension, and in different scales within them. Starting with the project dimension, this would either involve single researchers or labs or big research consortia. And here, these virtualization techniques would be important for collaboration, workflow transfer, data transfer, basically reproducibility. If you focus on the researcher dimension, going from student to PI, we have comparable factors like continuation of projects, workflow transfer, data set transfer, and of course, overall reproducibility again. And you can already see how each and every single aspect here and interaction thereof would actually benefit from virtualization techniques. These techniques have three main types that you may want to remember, being situated on the spectrum from a bare metal installation to an isolation in depth, starting with Python virtualization, with tools and resources like VN or Conda, software container technologies like Docker or Singularity, and finally, virtual machines like VirtualBox or VMware. And if we bring back our data analysis factorial design 2x2, we can actually make the same for interaction style and what is shared in virtualization technique. So interaction style can either be graphical user interface or command line interface, and what's shared is either the operating system or specific software only. And as you can see here, there's different options like Binder and Conda for software only, and for entire operating systems, that would be Binder, VMs, or software containers. And here we're going to focus on the latter because ideally we want to share as much as possibly when we go down that road in order to make it as reproducible as possible. Important to outline here is the differentiation between virtual machines, which is something that some of you might have used before, and software containers. Virtual machines basically try to emulate a whole computer system that is soft and hardware, and they run on top of a physical machine using a so-called hypervisor, which you can see here in the architecture of the system. And the hypervisor shares and manages the hardware of the host and executes the guest operating system that runs on top of it. So the guest machines are completely isolated and have dedicated resources. Software containers, in comparisons, they actually do share the host system kernel with other containers and applications, as you can see here. It's thus referred to as kernel level virtualization. And each container gets its own isolated user space, and only the binaries and libraries are created from scratch, as you can see here. So containers are way more lightweight and faster to start up and maintain than virtual machines. With the leading application and system for this is being Docker. And again, a Docker container, if you talk about that, you refer to as a closed environment that will use the exact same software versions, drivers, and so forth, independent from the system it runs on. It's the leading software container platform, an actual open source project at the time, and it runs on Linux, Mac OS, and Windows. So you can use it across platform, which is really nice. Again, enabling you to encapsulate and share different computational environments. So the thing with Docker is that it can easily escalate privileges of a user on a given system, because you need to be effectively treated as a root on the host system, and this is usually not supported by administrators from, let's say, HPC centers and other comparable architectures, because there's a lot that can go wrong rather easily and fast. For this, there's a specific solution, software containers, called Singularity, which is specifically focusing on scientific and application-driven workloads that supports existing and traditional HPC resources. And the important part here is that in contrast to Docker, a user inside a Singularity container is the same user as outside the container. So you don't need to escalate the privileges there, as it's usually supported on HPCs. And another cool thing about these Singularity containers, you can actually run existing Docker containers through Singularity, with them being converted. So in summary, virtualization is great for sharing code, scripts, functions, pipelines with colleagues and everyone else without dependency issues, except for the virtualization software itself. You can automate large parts of your processing and rerun analysis with identical or changed parameters, making it very interesting for the problems we're going to talk about in a bit as well. And virtualization is important for reproducibility of your results and the evaluation of software and hardware parameters, because you can basically vary computational environments to a certain degree and investigate the impact on the respective outcomes of your pipeline, either classic data processing, pre-processing, or statistical analysis. Now, when you want to create and share computing environments, there is a set of central questions regarding the fairness of them that you should always ask yourself along the process. First of all, what's the software stack I need and what are respective dependencies? Should certain aspects be included in the shared environment, like scripts and or data? And where will the environment be stored? How is it managed? And where should it run? And obviously, all of these questions drastically heavily interact with one another. Focusing on the first question, what's the software stack I need and what are the respective dependencies? This, of course, includes the operating system and drivers, neuroimaging software and respective packages thereof, as well as programming languages and IDEs that you might want to include in your software container. And when you see and think about this now, you might already ask yourself, this seems very cumbersome and very hard to implement, especially in the beginning. Isn't there something that can help me? Well, of course there is. One of these tools, for example, is called NeuroDocker, which is actually a Docker image to a software container that targets the creation of Docker and Singularity images specifically for neuroimaging applications. So you might call that Dockerception if you're up for that kind of pun. NeuroDocker has a great documentation on there and a GitHub repository that you're more welcome to check out. And the basic idea is that when you want to build these images, these software containers, and share them, you can easily install a versatile set of neuroimaging software and versions of via NeuroDocker through respective arguments. As you can see here, this includes ANTs, FreeServer, SPM, FNI, FSL, and all of that is nicely integrated into this command line interface where you basically only have to utilize and call the NeuroDocker container, tell it to generate either a Docker or Singularity image, a software container, what operating system should be the base image from which you want to start, which libraries and binaries that you want to install, and specific neuroimaging software, as you can see here, for example, FSL, ANTs, and SPM. And this will all be parsed into this Docker file, which you can then use to actually create and then run and share your software container. This extends actually further because you can actually combine different forms of virtualization. Here, specifically, Python virtualization can be a part of that. So you can create a dedicated Python environment or multiple thereof within a virtualized computing environment. So for example, using the same software container we have before, with this little input, we can include a dedicated Python conda environment in this software container as well. Now going on to the next question, should certain aspects be included in the shared environment, for example, scripts, code, and or data? So when it comes to data, you could, for example, directly include this data into your software container during the build. So you just basically copy your data over and it's going to be in there. However, what we will recommend is get and manage your data via data lake, as we previously learned, and make it available inside the software container when you're running it. Comparably, when you want to include code in your container, you can also do that directly when you assemble the software container. But what we would recommend is get and manage your code via Git and GitHub, for example, and make it then available inside the container, because this allows you a bit more to keep track of everything that's going on. That is specifically version control referred to here. And last but not least, where will the environments be stored and how is it managed and where should it run? And this is basically bringing back all the aspects we talked about before. So for example, you can use NeuroDocker, the script and the Docker file you're creating with that, or the Singularity recipe, and you put that on a version control using Git and or DataLab. You can share and get software containers via dedicated repositories on the internet, that is Docker and Singularity Hub. And even better, you can share and get software containers on a version control via a repronym container dataset, which is something that we're going to talk about in just a bit. So bringing all of these back together here, we basically have a nice set of tools and resources for each of these questions to address them respectively. So there's a nice guideline and roadmap going forward. And speaking of which, we can add the specific set of tools, that is virtualization, as an important means to address and mitigate the problems when it comes to data processing analysis in an open and reproducible manner here. However, these things that we just talked about, that is software virtualization, software containers, the different aspects of running these things when it comes to reproducibility, there's actually another very, very useful and important aspect that comes with them that, however, only emerges when you combine it with the things we already learned before, that is standardization, specifically bits, because these allow you, if you bring these two together, standardization and virtualization, to create automatic workflows. And what this means is that if you have your different computational environments, all of those could be standardized in a way that they run on bits datasets, which will be called a bits app, that are created, managed, maintained in a certain way. Same regards for sharing them either on Docker Hub or Singularity Hub, and that can be run on different systems. And what it means in a bit more detail, we're going to go through now. Bits apps aim to address aspects of this common problem that is specific data sets and workflows that you need to run on there in order to do the most appropriate processing. You always have to readapt scripts and then change these workflows in order to work on your data when you get the data standardized. And you can package your software, like your analysis and processing pipeline, in a software container that then understands bits datasets. It really opens up the avenue for open reproducible analysis on open data, because each container and app that we talk about here can include a dedicated pipeline workflow where the input is a bits dataset. The pipeline and workflow uses virtualization via containers, and the output will be a bits conform standardized derivative datasets. And with that, what you actually get as a whole is standardization plus flexibility, because you can adapt workflows a bit more, and reproducibility because you can rerun them, because you all got it virtualized in software containers. And as mentioned before, they specifically focus on data sets that are bits conform, and they all entail basically a set of core command line arguments. So most of them cannot be run via a graphical user interface, but have to be run from the command line. Importantly, they should not depend on software outside the container, and as said before, should be openly hosted on Docker or Singularity Hub, these repositories to share software containers, and include specific version tags so that when you run a processing pipeline, analysis pipeline, your data set using a specific version, other folks should be able to get that specific version to rerun your analysis and reproduce results ideally. And just to sum this up again, bits apps really target the automated and standardized analysis that are reproducible, because we go from standardized data sets over standardized workflows and applications and software containers that can be rerun because of the container sort virtualization technology, and you get standardized outputs in form of bits derivatives. As you can see here, there's actually a huge amount of bits apps out there for all these different types of processing analysis you want to do, ranging from standard workflows that you might know, such as free server and SPM related ones, to rather maybe unknown advanced analysis, just as hyper alignment within a machine learning setting, or MindBoggle, which is an advanced structural processing analysis. And all of these are really open for you to obtain as a Docker or Singularity software container with all the specific versions. You get information if they are passing software management tests, and all available, and even way more than we could put here because the screenshot wouldn't be too small in that case, on the Bits app website. And just to present you three of you that might be interesting in your work, because they address common problems. One of them definitely would be MRI-QC, which is a Bits app for quality control of structural and functional MRI data, because we all know these things are hard and we're all not trained to do it. So the developers around Oscar Esteban from back in the day, back then Russ Poldrick's lab, started to work on this tool that does extensive, comprehensive quality control for both structural and functional images, providing you with a versatile range of image quality metrics that tell you how good and or bad your data really is. You get, as you can see here, intuitive output reports and summary statistics, so that even if you don't have a lot of experience doing quality control, it's easy for you to spot potential problems in your data. And there's even a pre-trained classifier to predict good or bad data quality. So saying that, oh, you should maybe exclude this or participant from further analysis, um, that you can run on your MRI-QC data. And again, all of that open for you out there. You can check the paper and definitely read the docs. Following on that, a bits app most of you might have heard by now is fMRI prep, addressing specifically pre-processing of structural functional MRI data, because we know through a lot of papers and our, I guess, your own work, that there's a lot of variation and problems when it comes to pre-processing. And we know a little change there can make a huge difference down the line. So fMRI prep presents you with an extensive and comprehensive pre-processing pipeline for structural and functional data with a versatile range of workflow specifications. And as MRQC gets you intuitive output reports and summary statistics, supports volume and surface data, different output spaces, and gets you basically all the potential compound regressors that you're interested in. As MRQC, you can, and every other bits app, as said many times before, you can easily get that as a Docker or Singularity software container and make sure to read the paper and documentation. Another bits app that would be more or less the logical succession of the ones we talked about before, and maybe not that familiar to most of you, is called FitLens. As in pre-processing and QC, we know there's a lot of things that go wrong, a lot of little gears and knobs we can turn to change the outcome in the end. And FitLens here at that point focuses on statistical analysis of task fMRI data. It's a pipeline, a workflow for linear models building upon bits derivatives and bits stats models. The latter we're going to talk about in a bit. And as before, provides you with QC and confounds, intuitive output reports, and summary statistics, so you can run your classic GLM in a standardized and reproducible manner. There's no paper yet you can read, but definitely make sure to go through the documentation and try it on your data. And just to put this into a different perspective of why this is actually useful and helpful to you and what it can do to support your daily work, if we go from standardization via bits, what we've learned about before in the previous session, you go over to pseudonymization in order to be able to share your data, given the data privacy regulations of the country you're in. You now have your pseudonymized bits data set. And in order to run a rather comprehensive processing pipeline from quality control over pre-processing and statistical analysis, if you use these bits apps, this is basically free command line commands that you got to run. You get all these informative output reports, super extensive information on your data set, and it's all reproducible through the software container. And just think about how much time you usually spend on each and now of these tasks. Now these can be more or less fully automized. And as said before, those are not the only bits apps. And specifically, when you think about MRIQC, FitLens, fMRI prep, there's a new project called NIPREPs, where even more of these workflows are being made and worked on. So definitely recommend to check these out. As teased on before, an important thing to mention as well is that all these bits apps and many more analysis and workflows are also available as a data-led data set. So with that, you can get all of the bits apps and these other analysis and workflows version controlled and archived, accessible and manageable via data-led containers, which is a container extension to data-led, the tool we learned about before. And these can be added to data-led data sets. So you can add a software container to a data-led data set. You can track the provenance, that is the inputs to your analysis or processing and the derived outputs. And there's this GitHub repository providing you with further information on how to utilize those. Now we were thinking about your own workflows, because there's all these different, focusing on Python here, potential software analysis packages that you can use either in isolation or combined in order to run your processing analysis. So what if there's no bits app or other standardized workflow analysis out there supporting your analysis? Well, you could just use these tools and follow the same guidelines and principles we talked about. So you take the software packages and functions and virtualize your workflow into a software container using either Docker or Singularity. And ideally, on the way, you would use workflow engines and managers such as NiPipe and Pydra in order to make this a bit more scalable and easily applicable. Another tool that addresses this is called Giraffe, developed by Tim Murick, which basically presents you a graphical user interface to these to this question where you can combine different software packages, pack it into an IPAP workflow, and then create a software container out of that. So going back to our 2x2 design focusing on reproducibility in data processing and analysis. One thing that we touched upon a few times during the presentation already, but not really focused on, is called provenance, capturing provenance in data processing. And this is an important aspect that's usually overlooked, but luckily more and more tools are coming out of it because we need to know what happened to what part of our data at each and every point in time in order to be fully reproducible. And one tool, to no surprise to you right now, just want to reiterate that to do that is data-led. Because again, you not only can do version control, manage data sets, but can utilize containerized applications, put them or add them to a given data set, and then track the complete provenance, that is the inputs, to the analysis or processing, and the direct outputs via this data-led containers extension. And you can expectedly, the comments that you run via this functionality will be added to, for example, the git log as comments to within your data set. So they are tracked and you can just rerun a certain part of your analysis again, or can change certain aspects and investigate the respective impact it has on the outcomes. And for this, please make sure to check the respective parts of the data-led documentation. Another resource that allows you to do that quite nicely is BrainLife, which we're going to learn way more about later, because BrainLife, as you might already know, integrates data code and computing, which just allows you to actually capture complete provenance. You can go from a raw data set, import it from, for example, OpenNeuro, or you can upload yourself to the final analysis. All the inputs and the outputs of all BrainLife apps, basically the same idea as the BITS app, but a bit more flexible and free, those are tracked as well. So you can basically provide that as a file within your final publication, which apps you use, data and outputs. And this is all put together in these BrainLife data sets. So this allows you to rerun all conducted processing step right the same computational environment again, which is very useful. And for this, please go on to check further, go on the BrainLife website. And an important thing to outline here as well is that this is all a graphical user interface based resource. So if you're a bit, maybe not afraid, but not a big fan of programming at this point in time, and you prefer the graphical user interface, definitely make sure to check out BrainLife. And the last tool we want to present and talk about here is called Boutiques, which is a framework that focuses on making data processing analysis fair. So again, findable, accessible, interoperable, and reusable, because with Boutiques, you can automatically publish, integrate, and execute applications across different computation platforms so that you then can simulate, validate, evaluate, and for a given application that you're working with, monitor the different processing options and outcomes you have. And the deployment, again, works via software containers. There's a paper from 2018 called Herholz, and also make sure to check the Boutiques website. So we can now add these tools, BITS apps, BrainLife, to this part of our section, and importantly, add this little, but yet very, very super important addition of version control to our data lifecycle graphic. And this brings us to the last part of this section, where we're going to talk about statistical analysis within the interaction of data processing and analysis and open and reproducible neuroimaging. Because so far, we almost solely focused on reproducibility, this one quadrant here, but we know there are three others that we need to talk about as well: replicability, generalizability, and robustness. And we already briefly addressed potential methods and approaches to mitigate and address the risks present in each of those quadrants. However, here we now also want to present you with specific tools and resources that will help you to incorporate that into your workflows as well. And before we go into specific methods, we're going to actually go back once more to the standardization aspects, because there is a very, very important extension to BITS, that is the BITS stats models. which extends bits to capture and describe statistical models, also standardizes the terminology related to these models, because we all know folks talk about the same thing in a statistical model using vastly different terms or the other way around. And importantly, it's human and machine readable specification of statistical models. So rerunning a given analysis should be comparably straightforward to implement. As you can see, bit stats models basically incorporate the same guidelines and principles as the bits raw standard specification that you already learned about. And the way it looks like is you can basically see here where all these different aspects of the statistical model is written down in a JSON file. So that is more or less comparable to the metadata JSON file that you learned about regarding bits raw data sets, but here it encapsulates the statistical model that was run. As you can see here, this is basically done using three levels. First of all, the run under session level, that is within a given participant or subject. Then we basically pool across the different data points from the first level. Again, still intra-subject participant, and finally go to the last level, the dataset level, where you basically run your model across participants and subjects in your dataset. And I highly encourage you to check out the corresponding website, which has a lot of more explanations, very useful examples, and how you can implement that yourself. Which brings us to another thing we already talked about, FITLINS, because FITLINS uses the bit stats model specification. And just to reiterate that, to see how it all comes together, it's not only standardization and virtualization brought together for data processing and analysis in an open, reproducible manner, but FITLINS actually is a tool that allows you to do that, to apply these principles to statistical analysis already. So just once more, definitely recommend to check this tool out and try it on your own data. And the discussion about statistical analysis brings us to this rather recently introduced new method and or approach to statistical analysis called multiverse analysis. As outlined many times throughout this presentation and the prior ones, and also we will hear it again in the subsequent ones, there's a lot of sources of analysis and results variability, because each and every single aspect of your scientific workflow matters, and changing certain parts of it might have a tremendous impact down the line, for example, on your results and thus the interpretation. And therefore, all of these aspects should be as fair as possible. This concerns acquisition, data sets, metadata, as well, of course, your computing environment, as we talked about here for quite a bit, including the operating system, the software packages, version numbers, and so forth. And specifically, mega and multiverse analysis demonstrated the need for all of this, that is, fairness and standardization. Just to briefly mention two very important and highly related research outcomes concerning this. One that you might be aware of is the NARPS project from now 3 years ago, where Rodham was actually one of the leads spearheading this initiative. Here, a set of analysis teams, I think it was 60-ish, all got the same data set and were tasked to investigate the same hypothesis with rather interesting results that we're going to dig into a bit more in just a few seconds. And another one that's currently still ongoing is the EEG Manulabs project, where I think the first results are going to be published early next year, if I'm not mistaken. But going a bit further into the NARP study, again, different analysis teams, quite a few people as a whole are in there as a result of that. We're given the same data set and we're told to investigate the same hypothesis. And that's it. They could choose any pre-processing, any statistical analysis to investigate that, to do the processing and analysis. And what you see here is basically a plot showing how similar the resulting brain maps after analysis were across teams. As you can see, while there are a few big clusters there, there's also tremendous differences in there. And all of that, of course, is not only motivated by these different the choices that you have in processing analysis. But interestingly, there's also quite a few things that were found out regarding if certain hypotheses were predicted to be true or were said to come out true in the end. And that's the difference between team members and non-team members, external folks that participated here as well. Which goes a bit back to one of the potential biases that we talked about in the beginning. Another interesting study going along the same road is from 2021, Boring et al., where basically the same idea was investigated. You use the same data set and you have a few choices regarding pre-processing and analysis. So for example, different software packages, different types of statistical models. And based on that, you investigate how similar and or different the resulting brain maps are. And as you can see here, in all of these examples, we're not only talking about a few voxels here and there that might be different, but we're talking about prominent differences in terms of huge portions of the brain either being significantly active, quote unquote, and are not. So this really stresses and outlines how important these multiverse analysis are to get more of a sense of the impact our choices in processing analysis have. However, it of course doesn't provide an answer to the question which one is the ground truth and which one should we use. But really, it's more about outlining how different things are and how much results can and or should be trusted. And related to that, we actually go back to a tool we checked out again, which is boutiques, because there in boutiques you can basically implement these sort of multiverse analysis in a rather straightforward manner, because you can use these different applications across computing platforms. So you can basically change between different software packages and computational environments to then investigate what is the result, what is the impact this choice has on my results and outcomes. So this allows you to implement multiverse analysis yourself, which is something, even if it sounds very vague and maybe a bit hard to do right now, I recommend checking it out and doing it one or the other way to just see for yourself how prominent a difference it can make. And last but not least, there is another great tool called fuzzy environments that actually goes back all the way to the beginning where we talked about potential sources of unreproducibility in computational environments and software, and specifically numerical instabilities and potential errors that might result, or problems, let's frame it like that, problems that might arise on that. Because with fuzzy, what you can do is you can do an uncertainty quantification in terms of perturbations, evaluations, and direct application itself via so-called Monte Carlo arithmetic. And the idea here is that you introduce certain perturbations, small and or big, into your code, into, for example, software packages you're using, so really at the base of these numerical instabilities and computations, and then you evaluate their respective impact of the results. And this concerns, again, numerical instabilities, but also noise, computational environments, and algorithms. So it's really bringing a lot of things together there. And here specifically, you can turn the bias you might get out of that into variance and that probabilistic machine errors that allow for you to evaluate a certain pipeline to really see at which point, if at all, results deviate in a certain manner, which is really this is an amazing tool especially if you bring it together with boutiques, for example, because you can really stress test these different choices all the way down to the numerical aspects of them. There is a documentation and a GitHub repository out there. You can easily install it and include it in your pipeline to see how much of a difference it would make in your case. And with that, we are at the end of this section where we talked about data processing and analysis regarding open reproducible neuroimaging, dealing with different software and computational environments, reproducibility thereof. However, also the other quadrants we get to know: reliability, robustness, and generalizability. We talked about standardizing workflows using computational environments and standardization in terms of data that need to come before that, ways to improve statistical modeling in terms of openness and reproducibility and fairness, and started looking into multiverse analysis that allow us to evaluate the effect of different choices in pre-processing on our respective outcome measures. And with that, I'm done. I would like to thank you for your attention and hope you have a great time in the rest of the course, which I'm sure of.